forced oscillations then. Now, up until now we've looked at free oscillations. We set the pendulum in motion, we set the mass on a spring in motion, and we just let it do its thing. Now let's imagine we take our responding device, the key term here is responder, and this is the thing that is being made to vibrate. And we cause it to be driven so this might be child on a swing is the responder, and person pushing the swing is the driver. Now, you know that if the swing is going to be a successful experience for the child, then you have to match your pushing not only to the frequency of the child on the swing, which, as we know, depends only on the length of the swing, period being 2 pi root L over G. So as long as we're on the same planet, then the length of the swing dictates the period of oscillation. But it's no good if the period of oscillation is 1 second. If you are pushing once a second, but you're pushing when the child isn't there, when the child at the far end of their oscillation, if we were to picture that. So if the child is there and you, this is not to scale, are pushing at this point, well, that's going to do no good, right? It is only when the swing is here and you push that it's going to have any positive effect. If when it reaches the top of its swing, its maximum amplitude, maximum displacement, then if you push forward at that point, then you'll add energy to the system and the swing will get greater. And if you keep adding your energy at that point, if you keep driving at the right frequency and in phase, then you're going to get a maximum oscillation. So here we are driving our responder at the natural frequency of the responder, and we get a maximum amplitude. We get a maximum amount of energy in our oscillating system. You can imagine if you don't match your swing, and indeed you will know if you've ever done this, if you don't match the point at which you should apply your force correctly, so let's say the swing is coming back, and before it gets back you push, then the effect of that will be to remove energy from the oscillating system and the swing will slow down. This is what we do when we decide it's time for the child to go home and the child does not want to go home. We stop the swing, and we do this by applying a force which does work, removes energy from the system, stops the swing. But if we want the swing to get a bigger amplitude, then we apply our force at the maximum displacement at the amplitude of the swing, and by putting energy into the system, we increase that amplitude. So there you have forced oscillations where a responder is being made to oscillate by a driver, as opposed to free oscillations, which we've had in our previous videos. And in doing that, if the driver is in phase with the responder and it is driving at the natural frequency, you will get a maximum amplitude. Now, this happens in all kinds of different ways. I'm going to explore a few of those in our next video. Okay, so let's look at resonance now. We've looked at free oscillations, mass on spring, pendulum, simple pendulum. We've looked at forced oscillations, where an object is being driven, a responder is being driven to oscillate at a particular frequency. And we touched on the idea that if that driver has the same frequency as the natural frequency, that's a key term, of the responder, and it's in phase with it, then you get this maximum amplitude, maximum amount of energy stored in that oscillation. That's called resonance. Now, I've got a graph here of amplitude against frequency, and you can see on the graph that the amplitude doesn't do much, and then at a particular frequency, as you approach that frequency, the amplitude of the oscillation rises. You get to the natural frequency and the amplitude gets to a maximum. As you go past that, it falls. The amplitude falls down to a low level. This isn't necessarily zero over here. And then at another multiple of the natural frequency, you get another resonant frequency. You'll notice the amplitude is lower here, but you have a second resonant frequency, and then perhaps a third. Now, this happens in a number of different places. For example, if you had a badly balanced wheel on your car, if you've ever had a tyre changed, you'll notice how they don't just take the old tyre off, put the new tyre on. But what they will do is to take the wheel, put it into a machine which spins the wheel quickly. It then stops it and tells the operative how much mass to place and where on the rim in order to balance the wheel, literally to balance it. And the problem is that the mass is not evenly distributed in the tyre, or perhaps even in the wheel, but more likely to be the tyre. And so if you don't do that, then your tyre and wheel combination become, in effect, a mass on a rod. And you can imagine spinning a mass on the end of a rod. As that spins in a circle, it's going to be a very lumpy experience. And so you get this vibration in the wheel. Now, even if that doesn't make itself apparent to you, what you're getting with your wheel, if it is badly balanced, so there's your axle sticking out of your wheel, what you're getting is vibration in the wheel, which is damaging the wheel bearing in here, is damaging the steering bearings if we're on the front wheels here. And so that damage, and of course because the tyre is vibrating, it's wearing the tyre as well. So if you look at this graph, you have a low level amplitude all the time. It's only at particular frequencies it gets very big and perhaps noticeable, but it's always there. So it's always doing some damage, and sometimes it's doing maybe quite a lot of damage. So badly balanced wheels are an example of resonance. At a particular rotational frequency, you hit the natural frequency of that system, and so you get a maximum amplitude. So you have a particular frequency giving you a maximum amplitude, which in this case is down to a particular speed of rotation. So badly balanced wheels are an example of resonance. It would have to be very badly balanced for you to see these three. With your badly balanced wheel, typically you'll see one maybe at 60 miles an hour and then maybe another at 120. So let's say 30, 60, 90. So you wouldn't normally be up here. And if it was happening at 30, it would be very badly balanced. So badly balanced wheel is an example of resonance. Wind instruments, another example of resonance. Loudspeakers, you'll notice that a loudspeaker for hi-fi generally is not just a speaker on its own, but it has a cabinet, and the cabinet is designed to resonate. So, and thereby give you a bigger amplitude of sound. That's resonance in a free oscillation environment. Let's look then at a damped environment. So here we have a different situation, and you can see the amplitude rising at the natural frequency, maximum amplitude, and then it falls again. Let's consider damping that then. So if we were, there we have maybe light damping. If we were to take, I don't know, let's say our pendulum, and it's air damped, and then we were to attach a piece of card to our pendulum, so as it swings, the air resistance is increased. So we get this, and notice how the amplitude is reduced and the width of the curve is increased. Now there are some who would say that the resonant frequency changes. Unless you're changing the length of the pendulum, that's not going to happen. But the width here increases, and the amplitude naturally, because of the loss of energy, falls. So there you have heavy damping, heavy air damping, really. So you have what resonance is when you cause a responder to be driven at its natural frequency. You will get a maximum amplitude. That is resonance, and a maximum amount of energy stored in that oscillating system. An example of that is a badly balanced wheel. Another example would be infrared spectroscopy. Now I think this is truly amazing. If you take a crystal, let's say sodium chloride, and you fire infrared into that crystal from a device where you can change the frequency, a signal generator, you can change the frequency of the infrared being produced. So you're producing the infrared and you're detecting the infrared over here. If you plotted a graph of the intensity against the frequency, then what you would find is lots of infrared being transmitted, and then suddenly the amount of infrared being transmitted falls. So what that tells you is that more of the infrared is being absorbed in here. What you're doing is you're making the molecules of your sodium chloride oscillate. They're all bonded together, of course. So what you've done is to hit the natural frequency of that system. T is 2 pi root m over k. This is basically a mass on a spring. So the frequency, of course, is 1 over 2 pi root k over m. Now, you know what your crystal's made of, right? So you know the m. And you've found the natural frequency, so you've found f. And you know pi, of course. So what you're able to do then is to work out the spring constant for that mass on a spring system. You're able to work out the stiffness of the bonds between those sodium chloride crystals simply by shining infrared through and detecting it and knowing what frequency you get this dip. So you can work out the strength of the bonds in a sodium chloride crystal using resonance. I think that's amazing.